you have limited memory, you don't have tension, anxiety. Your memory grows up, rubbish memory, the brain becomes lazy, then you feel pressure, tension, anxiety. So,
What? What is that behind? Actually. Just need plugging, okay? So the camera. So they won't see us. I can lock. You can just use your code to log in, okay? My passcode.
the file is the one एक शीट है ओ तभी तो देखना English is
You just plug it in and then give a talk. You know what you're going to talk about.
Yep.
Oh.
Where is the USB?
Somewhere. This is
Right.
yeah, the same tool now. It's touch screen. You see that? It's not touch screen. Well, I like that one. I really hate the touch screen. I really hate the touch screen.
Yeah, it's not good. I don't even like in laptops.
Yeah, probably we see. You may want the other people to see you. It doesn't matter, so we can just make something like this. It's good. Alright.
Do I need to do anything at the end?
No, they everything automatic.
No.
All right, so the time stop. I'm going to make an announcement today. I cannot make the class today. That's the reason I have a special guest to give a talk about semiconductors and also AI. Okay, so the reason is that I have an emergency meeting just to sneak in from the National Institute of Standard and Technique. Okay, it's not a bad thing. It's a good thing. Okay, I'm not got the university best anybody. Okay, I'm not got the catch, but it's a good thing. Okay, but anyway, so that's the reason I cannot make the class today. Apologize for that, okay? But we're going to have a special guest to give the talk. And the content going to be covered, supposed to be covered by this class, will not be in your final exam options. Okay, make sense? And then we will going to have our regular class next Tuesday, have you to go through what are we going to cover. Okay, make sense? Okay, I'm sorry about it, but yeah. Okay, go ahead. His name is Tara Jatlaku.
Yeah, my name is Tara Jatlaku. And I'm postdoc in Dr. Lee's lab.
Thank you.
All right, sorry about it.
So, are you probably all guys from the first year or something like that? So, most probably you guys are from engineering department, right? And also most probably you guys are all working on kind of experimental research. All right, so I was PhD student under Dr. Lee as well, and at that time we were in Georgia State University, and as we were in like physics department, we were working on some kind of semiconductors there. And today I have like kind of slides which is related with semiconductors, and it is not thermodynamics. So it is just kind of out of the course presentation. So also another thing is that I'm not teaching any kind of courses, and I have not prepared for teaching. That's why I'll not know most of the things. That's why we can probably just share the information that I have and you guys might have. And the topic of my presentation today is semiconductor and quantum materials. Generally, like semiconductors are being used for like computation, or like kind of a device that works for computation. And lately, people are trying to replace or upgrade these kind of semiconductor materials with quantum materials, which is slightly different from semiconductor materials. Generally, like for the semiconductor materials, either it is like a processor or data storage device or whatever, it works under two states, either 0 or low and another high or 1. And it's a binary system, so whatever you do, everything is binary. But with the quantum materials, people are trying to like multiply the states, not only 0 and 1, also in between 0 and 1 as well. So it will have many states, and the computation will like speed will increase like in multiplications or exponentially. So we will have very fast computers that we can like do a lot of very high demanding programs or computations very easily, very fastly. But still there are a lot of challenges. That's why they are still not able to do a lot of things, or they have not progressed a lot on that part. And for the semiconductor materials that we are working, we have these kind of we had these kind of facilities when we were back in Georgia State University, and now here as well we are trying to build up almost similar stuffs, and also some different things that is useful for material science, or different kind of material characterization, fabrication, and other things. And here you can see a raw material synthesis setup. This is space that you can see some furnaces that is for synthesizing different 2D materials. Do you guys know what is 2D materials? Mostly you guys know, right? And we have different elements and they have different atoms, and those atoms are like in bulk material, they are randomly everywhere. But in 2D materials, they are aligned in a single atomic layer. And the one main example, or very popular example of 2D materials is graphene, which is a single layer of carbon. And some of the 2D materials have like maybe certain layer of atoms. Like if you think about like two element or two atom element, that is molybdenum disulfide, which is also 2D material, but those molybdenum and sulfide are like arranged in such a way that they have multiple layers, at least 3 layers, and that forms a larger plane. But for graphene, which is only single plane, like carbon and hydrogens everywhere. So when it was like first time they like knew there is carbon, no graphene. At that time, like they were thinking this is going to be like replacement of a lot of things in our daily life as well, because it was very highly conductive and also very strong mechanically as well. So they were thinking that we could be able to use in our daily life, like making these kind of chairs, very, very light but very, very strong. And there was also one kind of, I don't know if it was true or not, but they were thinking of building a
ladder that goes all the way up to the space. Because it's very light, so you can build vertically whatever length or height you want. And it's very, very strong, so it can support its weight very easily, even if it is very long. So they were thinking of building a ladder which can go all the way up to the space. Maybe they can send some vehicles or something like that easily. But still, like, the challenge is that it's very, very hard to synthesize. You can synthesize, or there is very easy method that you just use a tape and then peel it off from the bulk carbon, and you will get very thin layer or monolayer of carbons, that's graphene. And in the beginning, that was so easy. Maybe that's why they thought that you can make a lot of graphene. But later, they started working on that thing, and they couldn't find any method to make large, like, high production of that kind of a graphene. And there is a very another very popular method, which is
called chemical vapor deposition. So we vaporize certain chemicals and then deposit that chemical in single plane or single crystal.
that is done with this kind of furnaces,
And we supply different gases, and we also grow that graphene in our lab. And we do some kind of research that we use graphene and other materials to create heterostructures, and we study the fundamental properties, and also we do some applied research as well. And we believe that the graphene that we grew in our lab is one of the best around everywhere, like around the world. So we are recently getting certain, like, other people are getting interested in our method, and we have published certain papers, and they are asking about certain ideas, what we do to get that kind of high quality graphene. And also we have some collaboration with the electrical department guys, and they are fabricating some RF sensor, which is probably like supported by Army Research Lab. So it is related with defense. And they have got really good results. Whatever they were using before, they were not getting really good results, or like better efficiency than what previously people had. But with the graphene, they are getting very good results now, so probably they are going to publish a paper in Nature. That means it's kind of a very good material. And this is yellow light room, or it is also called clean room, where you can fabricate different types of devices or micro devices. And this is Raman microscope, which you can use to identify different materials. Like if you have a graphene and you want to know if it is really graphene, then you can use Raman microscope or Raman measurement, and then it will give like molecular signature peaks, and then you know what it is. And here is confocal multiphoton fluorescence microscope. It is like a kind of a system which can detect a single photon. Do you guys know what is photon? Yeah, it's like a light. Whenever we have light, we think that it is continuous wave, right? Because it falls under the spectrum, wave spectrum. So we think that it's just a wave, but there is one kind of a principle that they say that the light is also a particle. And that's called sometimes wave-particle duality. And we study those kind of things in quantum physics as well. And for that kind of phenomena, if we use this kind of like multiphoton fluorescence microscope or photomultipliers, then we can detect the single photon. And from that experiment or from that kind of measurements, we feel like the light is really a particle, not only a continuous wave. But if you do some other experiments like interference and other things, it is wave. And that's EFM, probably you guys know. what is AFM? Atomic force microscopy. It can scan or profile the nanometer scales of surface or materials. And probably you guys are seeing here that functional materials studio, that is our lab, and like we work with different functional materials and we do a lot of things, and one of them is this setup that we can use this setup to print like micro scale different things, and this is one print that we made, and you can see the scale 50 micrometers, so it is probably around 150 micrometer in like length. So the diameter of our hair is in average 100 micrometer. So this rabbit is inside our hair. And you can see on this side we tried to get the idea of the picture size it can make, and it was around 200 nanometer. So it can print very tiny objects. And this is our measurement setup. We call it cryogenic high vacuum chamber. And for the high vacuum, we can get up to exponential negative 9 torr. I don't know if you guys have any kind of idea about torr, but it's very, very low vacuum, let's say. And we also call it like cryogenic because it can go to very low temperature. That is because like if we do different kind of measurements, you know that if we have certain electrical component, let's say a resistor, and if you want to measure the resistance of that material or that resistor, then you have certain resistance at one temperature, and if you increase the temperature, the resistance goes up, right? Because there will be like different motion of the charge carriers inside, and then if they start like heating up, then that vibration goes up, and then they start bombarding each other, then they cannot flow freely. So they create that kind of resistance, and that's also a kind of noise. And when we are measuring very low level of signals, then if we have high temperature, then we get that thermal noise higher than the signal that we are looking for. That's why we need to freeze that material. And the temperature we can go with our setup is around 5 Kelvin. If you guys have idea of that Kelvin. So 273 Kelvin is 0 degrees Celsius. At that temperature you can freeze water, and then it goes down to like around 268 something degree below that temperature, below the freezing point of water. So it's very, very low temperature. And there is one phenomena called Bose-Einstein condensation, and that comes from very like popular or famous two scientists, something Bose and Isaac Newton. And what they have predicted is that if you cool down certain thing to 0 Kelvin, then that's called absolute zero, and at that time everything freezes, like even the motion of electrons. So that is absolute zero, but it is 5 Kelvin more than that absolute zero. So it's very, very low temperature. But this is not the best cooling or cryogenic system. There are certain groups that they have a system that can go down to 20 millikelvin. So that's very low. That is one thing we do. And with this setup, we can do on that temperature. And yeah.
Sorry, I didn't mean to stop you. I was just wondering, what's the threshold for when you start seeing electrons start to slow down in any significant amount?
We cannot see even any.
It's just on or off. Like as soon as it hits 0 Kelvin, they're just.
Yeah.
Like I know we can't get there, but they're just expected to be 0 from whatever speed of light.
Yeah, like you need to. I don't know what temperature you need to get down to see the slowdown of the electrons, but even with the 20 millikelvin, you cannot see that.
Okay.
It's still safe. And with that temperature and with that pressure, we can measure different characteristics or like different phenomena. Maybe even like we were even able to see the phonon oscillations of different crystals with that temperature and pressure in our system. That is what it is. And here is the evolution of electronic system. And it started with this vacuum tube transistor. Right now we have silicon transistors, but this actually started from vacuum tube. And inside that vacuum tube, they have, do we have a, oh, thank you. So we have 3 different electrodes, and let's say I exactly don't know the polarity, and if we supply, create a connection between these two, like if we supply a bias in between these two, then there will be certain level of current through these 2 electrodes inside a vacuum. And then if we supply heat on this electrode, or like filament, and then that heats up, that creates certain level of like thermal electrons or thermal charge carriers, then that will increase the current through these 2 electrodes. And that is how they used to control the flow of electrons between these 2, or control it, maybe switch it on and off or something like that. And like those were probably the size of this cap. And if you want to like create some kind of a logic circuit which can maybe add numbers like binary numbers, then probably you need to have multiple number of this kind of vacuum tubes and transistors. And that is just for like adding 2 digits. Let's say if you want to create a computer that has so many calculations and a lot of things, then they had to like build the network of those kinds of vacuum tubes, which would cover the whole room. And that probably was also very like low processing power. We cannot imagine right now, because like I don't know if you guys were like how old at that time. We used to use floppy disks, and those were really advanced as compared to these like vacuum tubes. And those floppy disks used to store I think around 1 megabyte, right? 1 MB. But these were I think few bytes only, like maybe hundreds of bytes. So we can imagine what kind of system it was. And then they started like they invented these kind of silicon chips or transistors, which would like decrease the size so much, and also which would require very low power or current. And then they connected those things, everything inside a package, and that's the chip. They invented chip. And then that was a kind of a structure which was not FinFET. And then they developed different kind of transistor which is FinFET. And finally, right now we have processor which is like trillions of transistors inside a single package. So this is how these things started. And here is the example of a very old, or like the transistor in the beginning. This one is like probably it was made by hand, like without using any kind of instruments or whatever. And it looks like this. They have like connections which are just wires, or kind of wires bent. And then they were able to create this kind of transistor. And then later they connected all of those things, making smaller sizes, and then first IC was something like this. And IC is, I think you guys know what is IC, right? It's an integrated circuit which has everything inside, like a transistor, resistor, capacitor, and everything, the combination of those things to do certain function. And this is oxide of different materials, which is similar to a glass. You can see silicon oxide or germanium oxide, and they made actually, like, when we talk about these kind of things, we need to know what is like a semiconductor, conductor, or non-conductor. A semiconductor is kind of in between metal and non-metals. It has equal number of electrons, no, half-filled outermost shells or orbits. That's why it has equal tendency to be not really a conductor, but not really a non-conductor. So if you add certain materials inside or mix them together with certain materials which has trivalent or pentavalent outermost shell, then it acts like a kind of a conductor. So these are called semiconductors, and germanium and silicon are very popular semiconductors. They use these to create this kind of NPN or PNP junctions. Here we can see that NPN and PNP transistors. Like P is P-type semiconductor, which is kind of a positive, which has more holes. Holes mean not physical holes, but the vacuum positions which can be filled with electrons. That's called hole. And electrons are another charge carriers, they can freely move. And those kind of two different materials are fused together or connected together. That forms a junction. They call it junction. And this can be like this kind of two junctions are made in a single structure, that is like NPN or PNP transistors. I think I'm talking a lot, but I don't know if you guys are enjoying it or not. Okay. So here is one image of silicon dioxide layer on top of silicon. And you can see the silicon here and silicon dioxide. And this can be probably, like this might be probably done with the TEM, tunneling electron microscopy. And with that you can see the lattice of different crystals, or like position of the atoms inside different materials. So these are silicon atoms, and this is the silicon dioxide atoms or molecules, but we cannot like differentiate those clearly. And like when you increase the thickness of oxide on top of silicon, you will find different type of color, and that is because of the light diffraction inside that layer. So you can see how, like you can guess how thick the silicon oxide is on top of silicon, because we need to use silicon dioxide substrates a lot. That's why I can say like if it is around 200 nanometer or if it is around 300 nanometer of oxide layer. So it can be differentiated with oxide color. And these are the developments over the different time periods. And we can see it started from very simple, not really simple. If you want to make this kind of IC, then it's still very hard, but it's simple if you compare with the other chips. And here probably most of the things are done within this one. But later with the advancement of the chips, they have like different clusters of different processors. No, like ICs to do different functions separately. Some parts store the data and some parts are computing and some parts are for the graphical computation and other things like that. And this is the what it is going on with the size of the different processors. Like in the beginning, we can see that it has 99 nanometer written here. That is the feature size or the minimum feature size they had inside the processor. And right now they are working for, I think, 2 nanometer. And for that, like, we can use very simple writing methods. Like we can use laser or UV light. And when we do in our lab, like maybe we can get up to hundreds of nanometer. Maybe 500, 600, something like that, nanometer with simple our setup. But to get the finer and finer feature size, you need to have a complex system. And right now there is only one company who builds, like they build this kind of UV system for processors. I think that's ASML. And if you check the like photos, then they have a system to write like just one wafer, which is maybe like 10 inch maximum. Not even 10 inch, I think. Like it's not very big. And they have a like machine which is almost as big as this room. So they use UV light and they use different lenses so that they can narrow down the feature, and also like they can filter the light bleeding and other things so that they can make 2 nanometer of feature size. But right now what they are saying is that even if you use like if you just use UV light, then probably it's impossible to go beyond 2 nanometer, 1 nanometer or something like that. That's why you might have, like you might sometimes hear about EUV. That's extreme UV. That means it's the lowest part of that blue spectrum. The wavelength goes down when you go like to the left of the spectrum. That is what they are using, and they are trying to go down. Probably they are like in the limit using just this system. Probably they need to like develop new kind of system that they can go beyond that. But the another problem is that, do you know what is the size of an atom? Probably angstrom. And if you think about nanometer, that is just 10 times, right? And if it is 1 nanometer, then there are maybe 10 atoms together on that width. So if you go, like, if they go beyond that, then probably like that is limited by the atomic size. Then they cannot go beyond that. So probably they are now at the like lowest level that they can go. That is also another reason that they are thinking about the quantum computing. And if you want to work with the quantum system, then you can just use one single atom, or maybe just one photon. So that is going to be the smaller size. And here you can see the structures of those kind of semiconductors, and this is AI, and I don't know anything about AI. And but what I can say is that right now, whatever phone we have are called smartphones, right? They are smart. And before that, there were like dumb phones, if you remember. Maybe, probably you guys were very small. And at that time, we used to have phones that you can just call and reset, accept, and maybe text.
they were dumb. They could not do anything smart. But right now we have smartphones that they can do a lot of things, and they are very smart, but they don't have kind of intelligence that they can decide something by themselves. But that's why they are trying to create some kind of system that is intelligent, and they can like make their decisions by themselves by creating some kind of logic and other things. They can give logic. So that is something that is like currently going on. And any of you guys, did you take any AI courses? No? But I think we need to take AI courses, right?
I have a
At
question.
least. Yeah.
I have a question. Sir, are
So-
you allowed to take AI courses under Professor Siddham?
I don't think he will teach. But I was also thinking to take AI course. Maybe there are some AI courses within the university, and if you are unaware about the AI courses and you have no knowledge, probably it's going to be hard to survive after maybe 5-10 years.
Do you use ChatGPT to write your paper?
Oh, not to write the paper, but yeah, definitely I use it for
Formatting?
some kind of refinement, or sometimes to get some information, but not to write the whole paper.
Obviously.
Yeah, and it cannot as well, because research is something new, right?
Yeah.
Maybe AI can, later some kind of advanced AI might be able to do. But that is going to be only kind of theoretical or computational.
But that's the baseline problem, right?
Yeah, yeah.
And the baseline is already set, and until unless they have the cognitive
Ability.
ability,
Yeah.
will not be able to think something new, right?
Yes. And if you think about these kind of theoretical or computational research and experimental research, and there is very large gap. Because for the computational system, you can just imagine, and if your computer can solve that or can compute that, then you can imagine whatever problem you want to solve. And if you start experimental research on that thing, a lot of things cannot be achieved for that, because there are a lot of limitations. And when we were working, when I was in Georgia State University, I was working with the graphene, and I was developing some kind of heterostructure between graphene and silicon. That is if you just think about that, that's very, very simple thing. Just transfer graphene on top of silicon, and then that you create the heterostructure. But that was really hard for me to do experimentally. And there were some theoretical guys, they were also working with graphene. And they were imagining graphene nanodots. They were thinking about creating a graphene which has, I think, 9 hexagonals of graphene or carbons, and then put them in a kind of array, maybe one here, with certain fixed distance, and then see the plasmonic effect of that system. And if you think about that, how to make that, you cannot make it right now, probably even in 50 years. That is, if you have this pen, and if you want to organize a nanometer of dots with this pen, it's similar to like that. So experimentally right now, the systems are in maybe 50 years late, but the computational or the theoretical system studies are 50 years. And yeah. So it's impossible, but AI can do that. And here is power demand for AIs. Probably it started from 2019, and it is projected until 2030. And in the beginning, there was no demand
of any power for AI, but right now, like in 2030, probably it is going to be around 20% of total power consumption, and maybe it is going to increase in similar like trend, and later a lot of power will be consumed by AI. And here is one map of the United States with power consumption level, or the amount of power they can consume, and it is compared with the power consumed by AI. And here is conclusion that the power for training ChatGPT 4 can support a family for more than 4,000 years. So that is the level of power it is consuming. But I don't think we need to worry about that, because they're using nuclear power, and if you just use like few grams of nuclear power. Okay.
They're also building a lot of like centers for powers in cities all over the United States, or like rural towns, and it disturbs people's sleep and things like that.
Probably, yeah. There will be always negative impacts.
And water.
And also, like, definitely they are not going to get clean energy for this kind of process. They are definitely going to use nuclear power, and that also will create a lot of negative impacts on environment or people or something like that.
But the positive side is that no family is going to survive for 4,000 years.
And out of nowhere, there was AI, and again, here is a semiconductor. This is again a transistor, and side effect of scaling. Like we were talking about narrowing down the feature size, and if you go really, really low, there is another drawback that's called like short channel effect. And the like, you can see here that the, let's say this one is source and this is drain, and there is a gate. This is like field effect transistor, which has always source, drain, and gate. And if they are very, very close to each other, then there will be something like this. The source and drain are almost connected to each other, and then the gate might not be able to control as expected, not precisely. That's why that is another problem. And here is also one power consumptions for like different years by the it's kind of semiconductors. And here is one example of computation, like computing architecture. And there are two types of architecture for the computation inside different computational systems. And one is von Neumann, which has a structure that the CPU and data and code are like the computation and data are in the same cluster. But in Harvard architecture, those are separately kept. So maybe this one is better because it can manage the both systems separately, and maybe it will be like faster for the processing, and also it can manage the energy consumption. And also here is kind of schematic and also examples of different transistor structures with different feature size. And this is the, I think, which has the highest feature size, 110 nanometer. And this kind of system is also like beginning of BEOL, that's his back end of line, which has a semiconductor structure, and also there will be structure behind that. And this is transistor, high K gate. High K is a dielectric constant, and we always use oxides as a dielectric constant, and they started using high dielectric constant gates. And also co-contacts, they tried to create like transistors together so that they can have common contacts as well. And this is lanthanum oxide in the gate, which is another oxide but which is different from the previously used silicon oxide, so it is different. And silicon germanium pin. This is another structure of transistor. Generally, like, there was one diagram here. These all of the PNP semiconductors are connected in a plane. So this is planar structure, but in FinFET structure, the source drain are in a single plane, but the gate is on top of those structures, so it looks like a pin. So it is called FinFET structure. And here we can see dipole materials for 2 nanometer. Dipole materials are the materials, they have a kind of asymmetric structure in their molecular structure, and they have they can create poles like negative and positive poles because they are not symmetric. Those kind of materials are dipole materials. They use those as a gate in these kind of 2 nanometer structures. And last, there is one example of 2D materials, MOS2, WSE2, etc. And finally, like right now, people are also trying to use these kind of 2D materials for the construction of different ICs. That is because, like, for the bulk material, you need to separate very thin line, like maybe few nanometers, let's say 1 nanometer, and then that becomes really tough because the molecules may not be like connected to each other, or even if it is connected, there might be some like disconnection and other things in that narrow line. But with the 2D materials, that is not going to be the problem because it's a crystal, so everything is connected everywhere. And if you can make thin features on those kind of 2D materials, then those are like confirmed to work. And that is also why we are also trying to do this kind of thing. Like this is similar, that you have a certain 3D structure in the base, and on top of that you use 2D material and you can fabricate. And another thing is that with the current system, they have everything in a single plane, or maybe there are like 3 layers maximum. And when they do that, let's say if you want to have like 1,000 different units, and if you spread them out in a single plane, then that will cover a very large area, right? But if you want to stack them in like multiple layers, like 10 layers, then you just have like 10 units, 10 units, and 10 units. That is going to be like, compared to the size that occupies in a single plane, it is going to be like 10 times smaller, right? But its volume will increase. But when you do that, what happens is that right now people are trying to like downsize everything. And if you can do that, then maybe you can do make certain like very small systems that you can put inside your body somewhere that can work as powerful as your computer. So that is also another thing that we are trying to do. And for that, for this kind of 2D materials, another thing is that if you have a, let's say, a layer of 2D material, then for the previous system, like for the silicons, you need to like remove something and put another thing in between to create kind of a difference, like let's say P and P. But with 2D material, you don't need to do that. You just create a certain area where you can grow certain material to convert that into N-type or P-type, whatever you want. So it is also going to be a lot easier to work with. But only problem is that you cannot make, until now they are not able to make any 2D material that is large enough to like work with. Maybe they can make once, but it takes maybe 1 day to just make one plane, and also maybe it takes $1,000, and that is not suitable for like production. That is another problem. This is also power consumption. This is a structure, and here they are also talking about negative K materials. Like K is dielectric constant, which is like kind of phenomena that you can create a charge inside something. Like when you rub this pen or plastic things, then you can create a charge inside, right? So that if you take it closer to the dust, it can pick up those dust because of the charge. So those kind of materials are dielectric materials, and the idea of creating charge inside those dielectric materials is that when you bring negative charge around this area, then positive charge will be collected on the other side, right? That is positive dielectric constant. But if you have negative dielectric constant, that thing becomes opposite. So they are also trying to use those kind of things, probably that has certain benefits. And there is also like computing systems that we have already discussed as well, this type of structures. And now here is another thing, that is floating gate. For this one, let me think. So generally this one is important for the data storage. And whenever you store data on any kind of storage device, that is stored as a charge. And when you want to read that out, the reading system will read each and every transistors one by one in kind of a system that still reads very fast. But one problem with that is like they don't have a floating gate, and the charge leaks through and you lose data over the long period of time. But they have a new system that is called floating gate. Here you can see floating gate, and this one is not connected to any kind of software or whatever. So there is no chance of losing charge. That can like retain the data for forever. So that is another thing that they are they have now. And this is about memory. Same thing, I think. And here is one very beautiful picture. If you guys think if it is beautiful or not, I think it is very beautiful. And this is the quantum computer. Like I said before, that we need to have a very low temperature measurement system for quantum systems, because they are just like a single photon or something like that. And for that, if you have high temperature or very kind of system that has a lot of residues and other gases or other things, you cannot see any signal. For that, you need to have this kind of system. And probably each of these lines are the lines for vacuuming, and also probably there are some electrical cables and fiber optics and everything that is measuring or giving signals. And these are all inside very, very low temperature refrigeration. and that is how they are able to work with the quantum measurements. And by seeing this, we can already see that this is huge compared to the chips. Probably, like you can see here is one connection. Maybe this one is just one, like one transistor. And if you think about this size of this one, probably this is like actual size right now, this big. So you cannot have this big CPU, right? If you want to, like even if you can buy and want to keep it at home, then that will need a cryogenic system, which works with helium gas, highly compressed helium gas, and also very high vacuum, which needs to go down to -9, like exponential -9 torr. For that, you need to have a vacuum pump, and that will be a simple vacuum pump, which is like this big. And also, you need to have a turbo pump, which is similar to like jet engines. So I don't think you will have jet engine pump and like very low temperature system at your home. So this cannot be imagined as normal equipments that we can like have at home. And this is the very famous Schrodinger's cat. And I exactly like don't remember, but we had studied this one. And on this experiment, you keep a cat inside with radioactive material, and when you like imagine if it is alive and open to see it if it is alive or dead, then there is a chance that it can both be alive or dead, and you cannot say without seeing it. That means if you want to see something, then it depends on when you are seeing it and who is seeing it. That means inside the quantum system, you have a combination of both states, alive and dead. And if you want to know if it is alive or dead, then you have some kind of system called operators. And when you use that operator, then you can calculate something and you know what it is. And sometimes it is called like observer as well. That is how it works. But like quantum system is very, very narrow and like which has a certain limitations as well. And I think it is something like that. So these two have always uncertainty. That's called uncertainty principle of like quantum physics. And if you want to know the position exactly, and this one will have higher like uncertainty if this is low. Or like if you want to see a certain particle in fixed position, then it will have uncertainty on momentum. Like you cannot exactly say what is its momentum. And if you want to calculate the momentum exactly, then you cannot say where it is. It might be anywhere. So it is kind of a very confusing uncertainty principle inside the quantum physics. That is also one kind of like, we can say that's also related with these kind of things. It's uncertain. And here you can see that classical computation with 0 and 1 states, and also quantum computation with combination of 0 and 1. So it will have more states, and with increase in number of bits, the number of states will increase exponentially in quantum physics. So you can do the computations in exponential way or very fast. And here is one thing called superconductors, and whatever material we have that always has certain resistance, but superconductors are the conductors that they have no resistance. And that is something like if you have let's say a round track, and if you have a train that can go round and round, and if you push once and then it goes forever without any energy, that's something like a superconductor that has no resistance. And like if you can have some superconductors in normal temperature or room temperature, then you can do a lot of things with like almost no power. But right now it is impossible, and people can achieve this kind of superconductor properties at very low temperature only. And this is also one example of superconductor idea, that you can have the magnet levitating in the air at low temperature with liquid nitrogen vapor. And this is talking about the quantum bits. That's another thing with superconductors. And this is one thing which is really famous, Hall effect. Have you guys taken any physics courses? Maybe some of you, right? And there is one very popular or like a very useful principle, where if you have a certain conductor and then apply electric field in between these two, let's say negative, and you have a magnetic field going through this. You have a conductor, and if you apply magnetic field and also electric field on the other side, then you will have a certain voltage across these two sides. That voltage is generated across those opposite edges. That voltage is called Hall voltage, and this Hall effect is very, very useful for studying the different quantum phenomena. And for the quantum phenomena, I think you guys know how the electrons are arranged inside an atom. They have different orbitals and spin. So if you want to see the spin effects or the different signals due to the spin, then you need to use this one, this system. That is why it is here. And here you can see different type of Hall effects. First one is quantum Hall, second one is spin Hall, and last one is anomalous Hall. These are different.
I have a question. Like in the quantum state, it can exist and non-exist at the same time. So how do we control something like that? If we even don't know if it is existing or not existing.
That is like it's kind of like quantum physics is always not straightforward. It's I took quantum physics 3 times because I had to do masters 2 times, and I also took quantum physics when I was in bachelor's. But still, I do not understand clearly. I always think that this kind of like abstract art. You do not understand it, but you feel like it is like interesting or nice or something like that. And for the existence and non-existence as well, something is there or not there, you don't know until you see it. And you see it means you operate that system with certain operator. They call it operator. And we have, excuse me. As an example, you can see here, this is momentum, this is position.
if you want to see the position exactly, then you need to have a operator which is called position operator, and if you do that position operator, you will see the position exactly. Not exactly, but close to exact. But at that time, you will lose the information of momentum. It's very widely uncertain. So you can see this as a certain, but this becomes uncertain. So it is existing, it is not existing.
And another thing is that, like you mentioned that, so now there is like 1 nanometer semiconductors. So if this quantum computing fails, we're kind of very stuck.
Probably. Probably then this system will be stuck that like level. Then people will start thinking about alternatives. And quantum is one alternative. Probably there are some other that we don't know yet. But definitely we will have alternatives. Right? Because people are very smart. They will always find solution for some problems. And fusion of dissimilarity for the future, VLSI. VLSI is very large single integration. And for this, you can see here, I have like 3 different or 4 different images here. First one is soft material, hybrid material, electronic material, and quantum materials. Let's see about this one. This is some kind of crystalline structure, which is probably a 2D material, and you connect that with soft material so that you can have soft, flexible, or stretchable structure or processor or sensor. And also similar kind of like 2D materials and other things also can be like stacked together to make hybrid materials. And electronic materials, this is probably a color sensor. And for the color sensors as well, they have different layers for the storage and also for the sensing of the colors. But in some silicon structures, but right now they are trying to use some kind of 2D materials underneath so that they can store and process the sensors data at the same time. And also quantum materials. Quantum materials are almost similar with the 2D materials. Those are just kind of used for like very small quantum signals. And this is one flexible device. And here you can see again a quantum computer. And this is a micro robot. And this is neural network that mimics the probably kind of human intelligence or brain, something like that. Is that all? Thank you. And again, there is one slide. Okay, so this is the system that we have, and here you can put your sample, and then there are probes to connect with the sample, and this will be enclosed from outside with similar metal cap, and we put sample here and then do the measurement at very low temperature and very low pressure as well.
What kind of insulating material you are using to insulate the outer environment with it?
With this one, when you lower the pressure all the way down, then you will remove almost all of the atoms or air or gas, whatever, around this area. So it will be insulated by itself. And there is a cooling head inside, which has a connection to the top, or here maybe you can imagine as a bottom, which is like built by the company itself, that which will be always in low temperature. So outer layer is not connected with the inner cooling head, and that is always very cold. because that is controlled from the outside compression chamber or helium. And then there is like gap from the outer this shield. And here we can see the gap, right? And when you like bring the pressure all the way down to negative exponential negative 9 torque, there is almost nothing. That means there is nothing to like conduct the heat.
Okay, so what they use to cool the system?
Liquid helium.
Liquid helium, right? So it has a mass, right?
No, we can see. I'll show you here. So this is, let's say, cooling head. This is compressor, cooling head, and sealed. Let's say it is sealed like this. So we have our sample here and probably connections something like this. And these ones are like made with relatively very low heat conducting materials. And now this one will like compress the helium and also expands. At that time, I think you know how the refrigerators work, right? And at that time, like this compressor compresses and expands the gas. At that time, like cooling takes place. And this one cools down to very low temperature. But like if you, like you are saying, if we have air or something here, then that temperature will be like directly conducted here, and this one also should cool down, or this one will heat up this one, right? But there is a vacuum system that pulls out almost everything from this area. So there will be no any particles, almost no. There will be always some particles, but almost nothing. At that time, the heat will be always conducted with certain medium amount.
Only because of the environment is already cold. That's why the system is cold. Do you mean that?
Environment means around
Means somehow we cool that.
this area or this one?
That one, yes.
This one, yeah. This one we need to cool
It's
it.
already cold, right?
Yeah, you can say already cold, or when we start this one, it starts cooling down.
So do you vacuum after that or after?
We vacuum first.
Okay.
We vacuum is first, and then when the vacuum is very low, then only we start cooling down. Interesting, right? What type of lab you're working with?
Oh, me?
Yeah.
Electrochemistry. AMPAC, Professor C. You know, the
I
department.
don't know almost any professor except my professor.
The
Because-
department chair.
Because when you are like postdoc, you don't need to take any courses. That's
Oh,
why
yes,
you
yes,
just go
yes.
to lab. You don't know anything.
How long you been here?
It's been, I think, 8-9 months.
Oh,
So I don't know who is department chair, who
so
is
you
director.
mean you were spending your like all the time in the lab?
Mostly, yeah. And we were like,
Very productive.
we just, our lab is new, so we
Yeah.
had to build it up from nothing. That's why I was just working as a labor, not a researcher.
No, but it's gonna pay you off anyway.
Yeah,
Future.
I know how to build up lab now. I don't know
Yes.
any research.
Yeah.
So if I'm going to be a professor or research or something, I can do it.
Yeah, I'm sure you will.
No, I don't want to.
Oh.
I want to do some job like which doesn't have any mental pressure. So I don't want to be a researcher. All right, thank you guys. I think
Thank
is
you
it
so much.
is it time? Like our time is over?
Yeah.
All right. Thank you guys. I might not see you again. eraser here.
ये खराब ना भाई, ये खराब ना भाई.
But I see him a lot.
You know him?
I see him, but I don't know him.
Yeah, because your lab is on that floor, right?
Yeah.
The same floor, right?
So
Yeah.
we see each other in the kitchen.
Yeah, yeah.
Yeah, you can't see me. You know why? Because my lab is like far away from here.
But I work with bacteria. Biology, yes.
Yeah, but I'm pretty confused here. Like this cooling, right? It takes place because of the environment interaction, right? Not because there are some particles. So there is no conductivity of temperature, right?
Yes.
So there is no conduction.
No.
So how the environment cools? Because after we vacuum, we already remove all the particles from the system,
No.
right?
Not the environment cools. Only that cool head, that central part, only that cools down. And our sample is directly connected to
And
that.
also nothing is like 100% vacuum, right? It's still there will be some.
Nothing. Nothing is 100%.
So it's not particle interaction cooling.
Yeah,
It's
I think the cooling also like helps to remove if there is any particle or
Yeah,
something, right?
like it freezes, so it is not.
or
Yeah.
if we have a system with a fixed volume and we reduce the pressure, we remove all the pressure, right?
Yeah.
Then automatically it cools, right?
That's also one. Like because it's ideal. When you study about ideal gas, it's
So you
easier
use
to
it.
add.
Mm.
What so I was
We-
asking whether it is environmental like
Yeah, I think for
Phenomena
example,
or-
in the TEM, for example, we use liquid nitrogen, right?
Yes.
We cool it down
Yeah.
for like to freeze the particles and everything.
yeah. So actually the nitrogen does not go to the system
Yeah.
inside the system.
No, not inside.
So
Yeah, yeah.
so that was the question. Like how does it exactly cool? Okay, maybe I can go through later by myself.
So what if